Here we go, Mighty Mouse. We're doing 1/6 factoring by grouping and the composition of functions day 1. And I found this great example on the internet and I just thought I'd put it on here, showing a factoring by grouping. I love the colors and the way that they put it together. So anyway, to factor by grouping, the way we're going to do it here is we're going to actually have 4 terms. And we are going to factor the first 2 terms, you see the purple, and we're going to factor out, use a common factor out of the last 2 terms. And so that's what they did. The first 2 terms you can see has a 2 and a w in common, so you factor out the 2w. 2w times what is 2wx, so you can see this is an x. 2w times 5 would be 10w, so you have this for this first factor. In the second 2, you factor out a 7. Factoring out of 7, x plus 5. And then what you'll see here there are 2 terms, and I'll mark them here. There are 2 terms, so you've got this and this. Well, what do they both have in common? Well, they both have the x plus 5 in common. So you factor that out, and then what's left is the 2w plus 7. And that, in a nutshell, is factoring by grouping. So factoring by grouping is a special case. You have to have 4 terms. It still might not work. So it doesn't always work, but it's a nice technique if it does. And anytime you have 4 terms, this is something I would do before I grabbed my calculator. So on this particular example, I have 8r to the third minus 64r squared plus r minus 8. And so I'm going to divide these into 2 pieces and factor out if there is something to factor out from both terms. So in the first set, I have an 8r squared. So I'm going to factor out an 8r squared. I'm left with r, and then a minus sign, and then an 8. All right, and then the second one doesn't have a common factor, so I'm just going to go ahead and write it. And to make it look like the other side, I'm going to go ahead and put parentheses. You can see now I have the 2 terms. They both have r plus 8 in common, so when I factor an r plus 8 out, I have 8r squared plus, well, I can't put a 0 there because I know I'm still using the distributive property. So r plus 8 times what, r minus 8 plus what is r minus 8, and that would be 1. If you'll notice, this does not factor, but if it was a minus sign, it would sort of factor. So anyway, this does not factor, and we are done. Same principle, different numbers. So once again, we have the first 2 terms, and the second 2 terms. In the first 2 terms, I'm going to factor out a 7 and an x squared. That will leave me 7x minus 5. And then I'm going to double check. So I have 49x to the third minus 35x squared. I'm good. Then the plus. That's the plus. And then on this one, it looks like probably an 8. So if I take an 8 out, that would be 7x minus 5. Now, when you're factoring by grouping, I'm going to give you a lot of problems that factor by grouping, right? So it's going to work. So if this said 7x minus 5, there's going to be a 7x minus 5 in the second group. So I have this. The common factor is 7x minus 5. And then what's left? 7x squared plus 8. Nothing factors further, and you are done. All right, let's move on from factoring by grouping to the composition of functions. And I wanted to start with a real-life example, something that actually happened to me this week and reminded me of the value of these types of functions and being able to use them. I think when we were introduced to composition of functions, we were introduced to notation. And what I'd like to do is just talk about an example. This really happened to me this week. So I went with apparel design program to the fabric store, and they were going there to purchase fabric to make some pajama pants. All right. So what they had to do was they had to buy some fabric. All right. And in this particular case, the PJs most of the time took 3 yards, so we'll keep it pretty simple. Okay, fabric you buy by the yard, right? So the cost per yard of this particular fabric that I found that was fabulous, I'm not even going to lie, it was awesome, It was $7.99 a yard. It was not on sale. Okay, so in order to find then how much the fabric cost, I would just multiply 3 times 7.99, and that would actually give me the total, the exact total for this. And I've got a calculator, and I'm just going to take a second to do that. 3 times 7.99 is $23.97. $23.97. That's a lot for pajama pants, in my opinion, but whatever. Okay, so that's not how much I paid. In fact, I got to looking at it, and there was a sign above it, and it said it was 40% off. Yeah, 40% off. Okay, so I'm taking this cost that I had, the $23.97, and I'm going to figure the discount on it. All right, and I'm going to write here, and I should write in a different color just so you can see. There was a 40% discount. Now, I don't really care what the discount is. I want to know what I have to pay for it. Okay? So if I get something and I have a 40% discount, then the amount that I'm going to pay is 60%. Does that make sense? You have 100%, take off the discount, I'm paying 60%. So I'm going to multiply this fabric cost that I had times 0.60 for a 40% discount. If it was a 50% discount, 0.5 obviously. If you're 25% off, you would do 0.75. And that's a really easy way to figure discounts when you're out shopping. So if I multiply that times 0.6, then my actual fabric is only going to cost me $14.38. That's still not the total that I'm going to pay, because now I have to figure tax. Now, honestly, I didn't really look up the tax rate, but I do know that I'm going to take the $14.38 from the last problem and multiply it times the tax. Now, once again, I don't want to know how much tax I'm going to pay. I don't care. I want to know what the amount is after I pay the tax. So here's another way of doing that. When I took a discount, notice that my decimal was less than 1. But to add tax, my amount is actually going to be bigger than the actual cost, right? So it's going to be bigger than 1. So what I'm going to do is I'm going to multiply 1.0817. I'm not sure if that's the tax rate, but I think it is. So when I multiply my $14.38 times 1.0817, it's about 8% tax, then my final total is $15.56. And then I told them, put a double line under it. That's what I'm going to pay for that pajama fabric. I have everything else at home. This is a composition function. This is a composition function. So let's think about this a second. X is going to be the amount of fabric that I use. X will be the amount of fabric. So if I'm doing a function, and let's just call it f of x, my original function will be x, the fabric, times the price per yard, which in this case was $7.99. This next function down here, computing the 40% discount, is g of x. And I find it by taking the amount I got for f of x and multiplying it times 0.60. Finally, this function, where I'm figuring my total, is I take the total that I got from g of x and I multiply it times 1.0817. So this is my inner function. F of x is my inner function. That's what I do first. What did I do first? I did f of fabric. So I write this down. I did f of fabric. That's what I did first. Okay, then I figured the discount. What did I figure the discount on? I figured it on f of x. So I took the amount that I had for f of x and put it in that, multiplied it times 0.60, and got g of x. My final total was I took all of that running total number, and put it into h of x. and found the idea. This is a composition function. Composition functions are where you take this amount that I got for this function, plug it into the next function, take that amount and plug it into this function. You work innermost out. That's a real-life example of composition functions. So algebraically, this is what it looks like. You have the innermost function. So I'm going to start with g, and I'm going to put a 0 in for x in the g. So g of 0 is 0 plus 1, which is 1. I'm going to take, I can rewrite this, f of 1. G of 0 equals what? 1. And then I put the 1 in for the x in the f. So this gives me 1 plus 2 plus 3, which is 6. So f of g of 0 is 6. So here's another example. If f of x is x squared minus 2x plus 6, to find f of 1, I'm going to place a 1 everywhere there's an x in the original function. So I have 1 minus 2 plus 6. And that's going to be 5. All right, so f of 1 is 5. Okay, so I'm going to come down here to this one down here at the bottom, and I'm going to say find g of f of 1. All right, so g, f of 1 is 5. So what's g of 5? Well, g of 5 is 5 plus 1, which is 6. So this equals 6. If I'm doing it algebraically, g of f of x means you start with g. So I'm leaving parentheses where the x is in g. And everywhere there's an x, I'm going to put f of x. So I have x squared minus 2x plus 6. If I combine this, combine like terms, then this would be x squared minus 2x plus 7. If I return to this find g of f of 1, then what I could do is I could put 1 in this problem and get 1 minus 2 plus 7, which is 6. Same thing. Okay, this is the same kind of problem, only graphically. This is doing this problem graphically. So we see here, this is f of x, this graph right here. This graph right here is g of x. It's a little hard to see, but that's what it looks like. Okay, so remember that if I have f of 3, right, then I would go to the f graph. This is the f graph, and I would find where x is 3. The y coordinate is 2. So f of 3 is going to equal 2. This would be the same thing as the ordered pair 3, 2. The 3 is the x, the 2 is the y. If I were looking for g of 0, I would go to the g graph, here's the g graph, and find where x is 0, y is 4. So g of 0 is 4. And so that's how that works. So that would be an ordered pair 0, 4. Okay, so in a composition function, remember that you're going to work from the innermost out. So it says here on this first one, g of 3. So I go to the g graph. The g graph is here. Find where x is 3 on the g graph and y is 1. So g of 3 is going to equal 1. So this gives me f of 1. So I go to the f graph. Here's the f graph. I go where x is 1 and the y is 2. And so the final answer for this is 2. Okay. When it says the composition of g of 0, we're going to use the same graph twice. So start with 0, where x is 0, and g of 0 is 4. So I'm going to just take a minute. G of 0 is 4. So instead of g of 0, I'm just going to put a 4 here. And then I'm looking for g of 4. So I come here to my graph. Here's my g graph. G of 4 is 0. So the answer is 0. This one's a little more complicated. F of g of 2. Still work from the inside out. So g of 2, I'm going to go to the g of 2 graph. So I go to the g of 2 graph. G of 2 is 2. So g of 2 is 2. All right, so I have f of 2. So now I'm on to the f graph. So I go to the f graph. F of 2 is 0. So f of 2 is 0. So the last thing I'm going to do is f of 0. So I go back to my f graph, find where x is 0. F of 0 is 4. So f of g of 2 is 4. So if you'll just take it step by step and remember what the notation means, this won't be bad at all. All right, there's one other type of problem that we want to talk about, and that's one that's already been done algebraically, and then you want to separate it off into two functions, an inner function and an outer function. So on here you'll notice that the inner function is going to be g of x, and the outer function is going to be f of x. So looking up at the example, you can see that you've got the fourth root minus 10. So that's going to be your outer function. So your outer function will be the fourth root minus 10. That's the outside. The inside function is going to be the 5x plus 7. Right? So in order to do the composition function of h, you're going to put the inner into the variable of the outer. Well, right now, outer doesn't have a variable. So we give it an x and then we're done. So if you had another thing, if you had another example, like say for instance, h of x was equal to the x plus 1 quantity cubed minus 3. And you wanted to put them in two functions such that the outer is f and the inner is g. So I'm going to write the inner first and then the outer. So this is inner and this is outer. All right, so the outer function is going to be something to the third minus 3. The inner function is going to be x plus 1. And then in order to put the inner into the outer, you put an x here and you're done. So you're peeling it in one function into more than one function. These are not piecewise functions, they're just composition, where you use one inside the other. And that's it for this example, and I'll see you in class.